Hi, my name is Isabel Faulkner. I am from Onslow College and I will be presenting problem number 4, loaded hoops. The problem states, fasten a small weight to the inside of a hoop and set the hoop in motion by giving it an initial push. Investigate the hoop's motion. Some highlighted words are inside the hoop, initial push, and investigate the hoop's motion. For us, an initial push was using a ramp to keep it constant. This is a video of the phenomenon. Notice how when the mass moves down, there is an acceleration, and when the mass is moving upwards, there is a deceleration. This is a table of key concepts. On the left, I have the linear form of that concept and then the rotational equivalent. So the first is velocity, and the rotational equivalent is angular velocity, notated by omega. For angular acceleration, this will be notated by alpha. The equation for linear momentum is mass multiplied by the velocity, and then the equation for angular momentum is mass times the velocity times the radius. For torque, this is force multiplied by a distance. So in the context of hoops, for a torque to be produced, there must be a distance between the center of the hoop and the center of mass of the whole system. A distance is made by having a load which changes the overall center of mass of the system. The last is centripetal force. So if you have a mass moving in a circle around a point, then there will be a radius, a velocity, and the centripetal force which is required for the mass to move in a circle. You can rearrange the equation for centripetal force to get this rearrangement, and this is a result of real forces, centripetal force, and it has to be provided from normal forces, from forces like the normal force and gravity. This is a picture of my experimental setup. I had a ramp which was supported by a jack, a piece of plastic which minimized the drop, and then a hoop was rolled down this. This is a force diagram of an unloaded hoop. The blue arrow is the radius and the green is the weight force. The center of mass has a linear velocity and the radius, which is equal to the radius of the hoop multiplied by the angular velocity. And there's also the angular velocity of the hoop. The angular and linear velocities are constant, and because there is no load, the center of mass and the center of hoop are in the same place. There is no distance between the two. Because of this, no torque is produced, so there is no angular acceleration. This graph in the corner shows a different distance time graph of the center of hoop, and it shows that the velocity is constant. This is a video of a unloaded hoop. So in comparison to the previous video I showed, it doesn't have those accelerations and decelerations going on. So this is a diagram now of a loaded hoop. The center of the hoop stays in the same place, but because a load is added, then the center of mass of the whole system is in a different place to the center of the hoop. Because it is not in the same place, there's a distance between the two, and a torque must be produced. Because a torque is produced, this must mean there is angular acceleration. So when the mass is on the right side of the hoop, the system will be accelerating. This graph in the corner is a velocity time graph, and it shows the sections when the hoop is accelerating. When the mass is going upwards, the angular velocity is still acting in the same direction, but the torque is acting in the opposite direction. And this is because the distance between the center of the mass and the center of the hoop is in the other way. So there will be a negative acceleration and the system will be decelerating. This distance time graph in the corner, it shows the sections where the hoop is then decelerating. We can combine these forces to make a force vector diagram. So the first is a weight force, and then the normal force, which is related to the friction force and the centripetal force. If you take out the weight force, sorry, the normal force first, and then the weight force, then the centripetal force is the resultant force of those two. So this is when the mass is at the top of the hoop. When the mass is at the bottom of the hoop, then the normal force is much larger, and the weight force is still acting downwards, and the centripetal force will now be acting upwards from where the mass is. And it is still the resultant force of the normal force and the gravity force. So this is the original force diagram when the mass is at the top of the hoop. So as the normal force gets smaller, then the friction force is also getting smaller. So as the normal force is getting smaller, the friction force has to decrease, and this means that there's not enough friction force, so the hoop will start to slip. When there is no normal force, then there is not enough of the weight force to provide the vertical centripetal force, and this means the hoop will then jump. This is a video of when the hoop jumps. In terms of energy, when the mass is at the top of the hoop, then it has its maximum gravitational potential energy and its minimum kinetic energy. When the load is at the bottom of the hoop, it has minimum potential energy but maximum kinetic energy. This graph shows that as the load height decreases when it's going from the right side of the hoop and down, then the linear velocity is increasing. And as the load height increases, going from the left side of the hoop upwards, then the linear velocity is decreasing. In summary, here is the video again. You can see that when the mass is traveling downwards, it is accelerating, and when it is traveling upwards, it is decelerating. These are my 4 parameters which I looked at. For every parameter, so for every test, I did 5 repeats, and the error is calculated using half range. For every parameter, I graphed the time period it took to do 1 full rotation and the maximum and minimum velocity. For every time period, it was the same. For every parameter, the time taken was the same, so I wanted to focus more on the maximum and minimum velocity. I looked into hoop radius, but I couldn't keep everything constant, so the data would be invalid. For data collection, I used Tracker, and for the time period, I took the 2 points and the difference between them to find the time taken for 1 full rotation. And then for the maximum and minimum velocity, I used a velocity time graph and found the maximum and minimum points on that graph. So for load mass, my prediction was that the time would be the same for every load mass, and this is because if you increase the mass, then you're increasing the acceleration, but also increasing the deceleration, so the difference would cancel out. For maximum and minimum velocity, when mass increases, I predict that the maximum velocity will increase and the minimum velocity will decrease. This is a graph of the period, and as you can see, the rotation took, with an error, the same amount of time. For the maximum and minimum velocity, you can see there is an upwards trend of the maximum velocity and a downwards trend of the minimum velocity. Next is hoop mass, and I predict that as the mass increases, the maximum velocity will decrease and the minimum velocity will increase. This is because if you increase the mass of the hoop, then you're changing the center of mass position and the effect of the load is decreased, so it's the opposite to increasing the load mass. As you can see, there is a downwards trend of the maximum velocity, however, the minimum velocity within error stayed the same. For initial velocity, I changed this by changing the height of the ramp, which would then change the angle. So my prediction is that both the maximum and minimum velocities would increase. However, that prediction is not reflected in my data. There is no trend. There is a general average trend, upwards trend of the maximum velocity, but the minimum velocity is staying the same. So I think if I tested more and got a more accurate average, then we might be able to see more of a trend going on there. So for my parameter conclusion, for all of the parameters time period, with an error, it takes the same amount of time. For the load mass, maximum and minimum velocity, as the mass increases, the maximum velocity increases and the minimum velocity decreases. For the hoop mass, maximum and minimum velocity, as the mass increases, the maximum velocity decreases, but with an error, the minimum velocity stayed the same. And for initial velocity, maximum and minimum velocity, there was no trend there. These are my acknowledgements and references. Thank you.